class, I'm sending you an auxiliary NMR IR problem. Again, the more you see of these, the better. I sent you 5 over the weekend that you should take a look at. The more you supplement this, the more you go through problems, the more problems you try, the better you'll get this. And you kind of learn something from every problem you do. And as you do more problems, you start seeing reinforcements of patterns that you've already seen. Okay? And you get better and better at it. Now this compound is C10H10O3. This is its spectrum. Again, I'm kind of drawing it, but it's not that far removed from what it would really look like. A singlet at 12, a singlet at 9.5, a doublet at 7.8, a doublet at 7, a triplet, 2 triplets in the 2 range. Now what are the areas of these? 1, 1, 2, 2, 2, 2. Okay? So it's not drawn to scale, okay, but that's what the areas would be for this. Of course, in every NMR, as you're probably discovering in lab this week, you put in some TMS, and TMS is the reference compound. So this would have a TMS peak normally, if you're running it normally. So the formula for this compound, C10H10O3, the first thing we do is get the unsaturation number, which would be 2N plus 2, so it would be C10H22O3. The difference is 12 divided by 2 equals 6. So this has a very high unsaturation number. And as I told you, put toward the top of your list benzene or aromatics, because that is very often the case when you have very high unsaturations. It's not, we have to prove it though. Okay, now I'm going to modify my IR. Well, I'm not going to, I'll modify it a little bit. All right, this is like a rough sketch of the IR. What I chiefly wanted to point out here is a very broad peak hovering around 3,000. I want you to think about what that means. Some jagged teeth in this kind of blank region that's usually sort of blank in the IR, and then a very strong peak at 1,700. Okay? I'm not going to talk about that again until the end because I don't want to let the whole cat out of the bag right now. But we're going to interpret the NMR very rigorously and then look back at that IR and see what that means. Okay? You will very frequently be given both an NMR, 1H, NMR, and an IR. Okay, now again, these are my drawings. So again, think about what that means. What does it mean when this is the most important thing I want you to get out of here. Very broad peak at around 3,000. Okay? So let's interpret the NMR. I'm going to have to erase my spectrum here. I'm actually going to erase both my spectra so I have some space. So let's just rigorously interpret that NMR. Some of these patterns you've seen already. Okay? So here's our table. Delta, area, splitting, conclusion. Okay? First peak. Okay? TMS. I don't care about the TMS peak. Next peak, it's at about 2, let's say around 2. Area of 2, splitting, triplet. It was a triplet. And you can, the beauty of a video is you can go back and look at that spectrum. What does that mean? The conclusion for that is that I am seeing 2. The most likely way to see 2 is a CH2. Okay? And the triplet means it's next to a CH2. Okay, so we have a CH2 that's influenced by a CH2. This position, by the way, is consistent with being near a double bond of some kind. Okay, not on a double bond, but near one. Okay? This does not indicate a particular functional group as of yet. Then I said a little farther down, but these shifts are consistent with this kind of situation, where you have an H on a C next to a double bond, and that could be a double bond O too. We saw that a little bit in class today. Area of 2, again, it's a triplet. Now what you're seeing here is really just the other CH2. So once again, I'm seeing a CH2 next to a CH2, but I'm actually going to identify that as this one. So we're seeing this talking to this, and then we're seeing this talking back to that. So that's perfectly consistent. There's nothing too extraordinary there. All right, so then we get down around 7. What does 7 say to you about shift? Now again, I said this means near a double bond of some kind. You know, some kind of double bond. This is saying aromatic. it should just be screaming at you aromatic. And again, the most prevalent aromatic ring is a benzene ring. That doesn't mean it's always a benzene ring, but most of the time it will be a benzene ring. And you don't want to go to something more exotic until you've exhausted this idea. Okay, so what is the area? The area is 2. It's a doublet. Now this is a pattern we saw in class last week. Okay, then at about 7.8, you have another 2, and you also have a doublet. Now you may recall from last week, what this means is that you have an aromatic ring, and the aromatic ring has 2 environments on it, and they're exactly the same, 2 different environments, but within those environments, the hydrogens are the same. Okay, 2 different hydrogen environments. This is also telling you that the total number of hydrogens on the aromatic ring are 4. That is the total number. What that means is you have 2 substituents on the ring. Again, it makes the most sense to first assume it's 1 benzene ring, because were it 2 benzene rings, the unsaturation would be higher, and it would be difficult to accommodate that with all these carbons. Okay, so last time, what we came up with for this last week, and we did a problem like this every day, we came up with this kind of pattern for the benzene ring. Now notice, you're going to see this coming up over and over again. Notice we are interpreting differently when we're at the high ppm than the low ppm. At high ppm, the effects are mainly due to pi circulation. And if you use the traditional treatment here, you would say 2 CH2 next to a CH. However, that doesn't work when you're dealing with double bonds or unsaturation. So these 2 are the same by symmetry across the ring. So these 2 are the same, and these 2 are the same. But each one in that pair is talking to one, so that's why you have the doublet. And what I suggest doing is looking at all the other combinations that would give you 4 hydrogens. All right, let's look at these other 2 peaks. There was a peak at about 9.7 or so, okay? This is one you'd pull right off a table. It's also one that I gave you in class. I told you this peak is consistent with an aldehyde, okay? And then this other peak is kind of interesting. This peak at 12, which again, these are area of 1, singlet. This one is a carboxylic acid. Okay? There are certain things that are more readily identified by their position than by their splitting and integrals. Okay, so this is saying 1 isolated hydrogen. There's very few things that are down at 9.7. Aldehyde is kind of like a sure thing with that. Carboxylic acid, sure thing. Now go back to the IR and realize the IR had a very broad peak centered around 3,000. And I don't know if you remember this from the landscapes or the topographies we did in class. This corresponds to the OH of a carboxylic acid, which has sort of a unique landscape. And then there were a couple teeth here which were consistent with aromatic overtones. And then probably this would actually give 2 spikes at around 1700. And this would indicate, and I'm not saying exactly at 1700, but around there. That would indicate carbonyls in the structure. So that's consistent with these 2 conclusions. Now you might have pulled that right out of the IR. You might have looked at the IR and said, I've got this, I've got an aromatic right away. That might have been clear to you right away. But regardless, you can interpret it without the IR. All right, so let's put our pieces down. How many minutes is it now?
Just 9.
Okay, good. So let's kind of put this thing together. This is what we've got. We've got this aldehyde. And aldehyde is, and I base that totally on the position. You should start looking at the NMR IR tables that are in your binder, okay? This has 1 connection on it, okay? We have a carboxylic acid. This has 1 connection on it, okay? We established that we had this little piece, a CH2, There was nothing too spectacular about it in regard to its positioning. They were both at about 2, which means they were probably near double bonds. The other thing we have is we have an aromatic ring, probably a benzene, with hydrogens that are likely to be disposed in this manner. Now, Again, I encourage you to try other combinations of the hydrogens. In other words, cluster them all together, put them, try different substitution patterns. I'll show you one at the end. But this is basically what we've got. This is what the NMR is saying. It's saying aldehyde, disubstituted aromatic ring, and this is called 1,4 disubstitution. A little piece like this and a piece like this. These clearly go in the middle and these clearly go on the ends, all right? You can only put it together two ways. So let's look at the two ways you can put it together. Okay? This is one way to put it together. Write your ideas down. Nothing's going to happen if you write the wrong structure. You can just go back and criticize it, and you'll always learn from that. So let's say this is one idea. And let's say the other idea is this. Let's say I put the CH2 over here, and I put the aldehyde next to that. Okay. Okay. There are subtle differences in the positions of the peaks because of these structural differences, but in many ways both of these fit the spectrum in the sense that this would give the singlet at 12, this doublet would be in the 2 range, this triplet would be in the 2 range, this triplet would be in the 2 range, this would give 2 doublets in the aromatic region, and this would give a singlet, okay? This would give the aldehyde peak at around 9.7. But there is one difference between them in terms of splitting, okay? In this structure down here, there's a problem. So if you're criticizing this, everything works. This works, this works, this works. The problem is with this, okay? This hydrogen is 1, 2, 3 bonds away from that hydrogen. That means they would talk to each other and they would split each other. The problem with this, if I were criticizing it, is that this H would give a triplet, and this H would give a doublet. I'm not a doublet, sorry about that. This H would give a quartet, at least a quartet, at least. Okay, because it's being split by these two and by this one, okay? That is not what we observed in the spectrum. In the spectrum, the aldehyde H at 9.7 was a singlet, okay? And this was merely a triplet. Therefore, this is a better fit, okay? Now, again, I tried to go through this. We tried to go through this individually with students in class, but think about what it would be like. For example, if I put these two groups, CH2, CH2, OH, like say I put that same chain down there, and then I put the aldehyde here. Think about this. H, 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 H. Okay? This NMR said there was only 2 types of aromatic hydrogens. If you really look at this carefully, this hydrogen here, if I called this A, this hydrogen would be B, because these are not the same. They do not have the same environment. And technically, this one is also different from that one. So that would imply a much more complex aromatic region. Okay? So tomorrow night, as requested in class, I'm going to do an alcohol, because I told you alcohols are a little funky, and I'll talk about that tomorrow night. But keep doing problems, and tonight we're going to post some answers to some of those spectral problems that you have. Okay? All right. Next video tonight is going to be a little bit about conformational analysis. Okay, that's it. See you in class.